And here you are coming back for more. You must really like it or have paid a lot of money for this course. Alright, let's wrap up chapter 1. There's not much left. There is molecular weight and the mole concept, and we are done. Okay, so we already have discussed and talked about atomic mass units. The mass of one proton or one neutron is 1.67 times 10 to the negative 24 grams, which is of course 1.67 divided by 1 with 24 zeros. It's a very, very small number. So we simply call this an atomic mass unit. So one proton is one atomic mass unit, one neutron is one atomic mass unit. And because electrons have 1700 times less mass, we essentially say that that is equal to 0. Okay, have done that already. We did it for boron. Where do these average atomic masses come from? This is the same calculation. Don't need to go into any great detail. If we're looking at carbon, carbon has an average molecular mass of 12 atomic mass units. It's based on 3 major isotopes. Carbon 12, which is 90, said it was 99% abundant, so 98.9% abundant. Carbon 13, which is 1.1% abundant, is a stable isotope. And then we have the carbon 14 dating. Carbon dating, where the radioactive isotope carbon 14 essentially is 0 here. It's like 0.0001, and that's enough for us to detect. But you add it all up, you multiply the percentages by their weights, their atomic mass units, and you come up with the average atomic mass. All right, so then we call something a molecular weight or a formula weight. Okay, so that is simply differentiating the different kinds of compounds. We have ionic and covalent compounds, and so the ionic compounds are have a formula weight, and the covalent compounds have a molecular weight. It's really just a subtle difference, and you won't know the difference between ionic and covalent until chapter 5. But in a nutshell, an ionic compound binds metals and nonmetals, and a covalent compound is an organic compound which has only nonmetals in it. All right, it's pretty much interchangeable and no big deal. All right, let's calculate the formula weight of iron chloride, aluminum nitrate, and the C2H4O, like acetone or something. So FeCl3, C2H4O, and AlNO3. And here you see, you've written here molecular weight. So this is just nonmetals. Iron is a metal, aluminum is a metal. So that's just the distinction there between formula weight and molecular weight. Let's do iron chloride. All right. So in order to do that, and you should get your periodic table out, one that you can use for your exam, so you know how to read it, you know how to find things. I'll just show you real quick. What we need is we need the average atomic mass of iron. So we need 55.85 AMU. One iron weighs or has the mass of 55.85 atomic mass units, and then chlorine 35.45. I'm only going to have this periodic table up. This is where the numbers come from, and so you should be able to find that. Okay, so then we have, in this formula here, we have 1 iron and 3 chlorine atoms, right? The little 3 applies to that chlorine, okay, only. And so in order to calculate that, we have 1 times iron, which is 55.85 AMU, okay, and 3 times chlorine, which is 35.45 AMU. This is still 55.85. calculators are legal, so use one. 106.35. Add it all up. That makes 162.2 AMU. Okay. If you've done this before in high school, if you don't need to practice that, you should skip the next few examples and pick up where the mole is. All right? Let's do C2H4O. So carbon is 12.01. So we have 2 times 12.01, which is 24.02 AMU. We have 4 hydrogens, 4 times 1.01, which is equal to 4.04 AMU. And then finally 1 oxygen, 1 times 16.00, 16.00 AMU. You add it all up and you get 44.06 AMU. C2H4O has a formula weight of 44.06 AMU. Aluminum nitrate. Now, aluminum nitrate, the NO3, is a unit that belongs together, and so it is put in parentheses, and then there's a 3 behind it, which means we have 3 nitrate ions here. Okay, so we have 3 times 3 oxygen atoms and 3 nitrogen atoms here, so that's not that difficult. So we have 1 times aluminum, which is equal to 26.98, which brings the total to 26.98 AMU. And every now and then I get a glitch, even on a $300 fancy tablet. We have 3 nitrogens, 3 times N. Each nitrogen is 14.014 AMU. Multiplied out is 42.042 AMU. And then we have 9 times oxygen. Each oxygen is 60.00 AMU, and the total here is 144.00 AMU. The cutoff for sig figs is here. Our answer is 213.0. Oh goodness, second glitch. 2 AMU. Moving on to the last one. Oops, that was the last one. The reason I have this here is because there's a lab that has you deal with a hydrate. Okay, you have Epsom salt, and Epsom salt has the tendency to take water up. Okay, so it's still going to look like a white solid, these hydrates, and water is incorporated and you don't see the liquids. And so the formulas are written like here. So you have this BaCl2 unit, and for every 1 BaCl2 unit there are actually 2 water molecules here, so 2 H2O, and that's written like that. So this is a hydrate, right? So this is a barium chloride dihydrate, di referring to 2 of the water molecules. And so when you heat this up, and you're going to do this in the microwave, you can drive off the water, and it's actually kind of cool the way that the Epsom salt cakes up in the microwave. You'll visually see that something has happened. You're driving off the water, okay? And so you calculate the molecular weight for that no differently than you would for anything, except you're also going to incorporate water, right? So you have 1 barium, 2 chlorines, and then 4 hydrogens and 2 oxygens. Here I've just taken the entire formula weight, or molecular weight in this case, of water, since that's a covalent compound, and multiplied. I already have that here. So, but anyway, you end up with 244.28 AMU, and you are going to calculate the percent water in the lab. So all you do is, of course, percent is part divided by total. So this is part water, divided by total times 100, so there are 14.75% water in it, except in your case you are going to have magnesium sulfate, and you're not told how many water molecules are in there. So you're going to determine that. So you're going to weigh out like 5 grams, 5.07 grams of the stuff. You're going to stick it in the microwave, and it's going to come out and weigh, to make my math a little easier here, 4.57 grams. And so you have 0.50 grams of this is then water. And then that would be your part, and your total would be that times 100. That would give you the percent water. And then you can, once you know more about the mole, you can actually calculate moles, how many moles of hydrogen of water are there per hydrate. Okay, time to talk about the mole. The mole is nothing but a number. It's just some number, okay? Just like a dozen donuts is 12 donuts, right? So it's just a number, and this is it here. And the reason for that is that if you have 1 AMU and you take that 6.0 times 10 to the 23 times, if you have 6.02 times 10 to the 23 protons, let's say 1 AMU is a proton, then that turns out to be 1 gram. Okay? And that's just a convenient number that turns 1 AMU into 1 gram per mole. Or if you have carbon, 12 AMU equals 12 grams. 144 AMU equals 144 grams per mole. That's the whole reason we have that. Okay? The author compares it to a baker's dozen. Okay, this is a scientist's dozen. Right? And so we have these numbers. And you may not have heard of a gross, but a gross is 144. And I got to tell you this story, so skip through it if you must, but it's a really good story. So I'm a beer maker, and so I have to cap my own bottles. And I never could figure out this gross. I think it was a silly English thing, It's just what do the Brits do? I'm from Germany. I do things in the metric system, right? So that's always good stuff, right? I never understood this 144, but I'm a beer maker, and so I get these caps, and there's always 144, and I wondered what that was all about for decades. And then one of my children kept bugging me about buying a dozen donuts. I want a dozen donuts. It's like, that's just crazy, right? And so at some point I did the math, and 12 times 12 is 144, and I said, oh, then it clicked on me. That's a case of beer is 48, so it just works out exactly for a batch of beer. This is great. So then I started really liking the gross. Okay, so but again, the Avogadro's number, this guy who came up with this large number, 6.022 times 10 to the 23, he did not make that number up to torture chemists or students. It's a really convenient number to upscale the atomic mass unit to something that we can weigh out in molecular weights. And so we are going to see these molecular weights more. We're going to deal with them more than atomic mass units, because we can put it on the balance and weigh it out and convert it. Okay? So this simply turns 1 AMU into 1 gram, right? And so if you look at the atomic mass of water, hydrogen here, right? If you find a periodic table that has more significant figures, it actually has an average mass of 1.00794, and so that would be equal to exactly 1 mole of a hydrogen atom. So 1 mole of hydrogen is equal to 1.008 grams of hydrogen. 1 mole. And that's a conversion factor, right? Whoa, what about 1 mole of sodium oxide? Well, all we have to do is we have to figure out what it is in atomic mass units and just change it to grams per mole, right? So the periodic table has 22.0 0.99 grams for sodium, or AMU for sodium. See, I'm already switching because I'm more used to that. And then we have that times 2 plus 16.00 grams equals 61.98. 61.98 grams of sodium oxide equals 1 mole of sodium oxide. Okay. And so then the molar mass and formula weight in grams, or equals the formula weight in grams. That's pretty simple. We can do calculations with that. How many grams of HCl, hydrochloric acid, contains 17.6 moles? Well, we need a conversion factor. We have 17.6 moles of HCl. Remember the factor method, the cancellation method, that's exactly what we want to do here. I want to know grams of HCl. So I need grams of HCl and I need moles of HCl. If I have for a single conversion factor, if there's such a thing, this is what I would have to have. So moles and HCl cancels and I have the grams of HCl that I'm being asked for. Well, the conversion factor is simply that of the molecular weight, which we can look up. If you look up, hydrogen is 1, chlorine is 35.45. So molecular weight of hydrochloric acid is 36.46 grams. 36.46 grams equals of HCl equals 1 mole of HCl. That's the conversion factor. You should be able to find that a lot faster than I did. Okay, so you put the 36.46 grams in here, 1 mole on there, and you have an answer. This would be 641, well, it's 3 significant figures, 42 grams of HCl. Alright, so moles to grams and grams to moles are converted by not Avogadro's number, but with the mole concept. Let's do another one. How many grams of iron perchlorate contain 1.670 moles? Okay, so we need the conversion factor. We need to find out, so we have iron and 2 times chlorine and 6 times oxygen. Okay, so you look that up in the periodic table, add it all up, and you get 222.75 grams. 222.75 grams of FeClO3 2 equals 1 mole of FeClO3 chlorate 2. Alright, so now we can do the calculation. 1.670 moles of FeClO3 times 222.75 grams of Fe blah blah ClO3 divided by 1 mole of the stuff. The stuff cancels, the mole cancels. See, here it might seem like it's not very useful to write the formula out, but when we do more complicated conversions, it's important that you do and take your time, because that's where students usually screw up. So develop a good habit, especially if you're going to take more than 1 semester of chemistry. Calculator tells me it is 372.0 grams of FeClO3. Okay. Alright, so now we have how many moles of lithium fluoride. contain 0.576 grams. Okay, so now we're going to have the same conversion factor, right? We're starting out with 0.5675 grams of LIF, and we want to go to moles. So we need to multiply by moles of LIF and divide by grams of LIF. Well, 1 mole of LIF is equal to 25.94 grams. And I got that from the periodic table by looking up the atomic mass units for lithium and fluorine, and I added them up and turned it into molecular weight. And that gives me, so the answer is 0.022. Let's do the significant figures right. Okay, 0.0218 moles, right? Because grams cancels, lithium fluoride cancels, and we have 1, 2, 3, 4 significant figures. 0.2188 moles of lithium fluoride. Okay, one more. How many moles of calcium carbonate contain 1.67 grams? So 1.670 grams of calcium carbonate times 1 mole of calcium carbonate divided by 100.09 grams of calcium carbonate equals 0.01668 moles of calcium carbonate. Grams cancels, calcium carbonate cancels, units are in moles of calcium carbonate, and we have 4 significant figures. Alright, now I'm going to throw you for a loop here. I'm going to ask for atoms. How many atoms are there in 1.670 moles of iron? Well, Avogadro's number means just that, right? It means that there are 6.022 times 10 to, okay, getting tired, 10 to the 23 atoms or particles or donuts equal to 1 mole of that particular substance, right? So in this case, iron. So now I can convert 1.670 moles of iron times 6.022 times 10 to the 23 atoms of iron divided by 1 mole of iron. And I put that in the calculator and I get 10.06 times 10 to the 23 atoms. So here I just took 6.022 and I multiplied it by 1.67, and I didn't do the 10 to the 23. And so I get, just to avoid the exponent, I think I highly recommended that you do that, and then you just keep that. That doesn't go anywhere, right? And then if you wanted to fix that, you just go 1.006 times 10 to the 24 atoms. But you can, of course, use your exponent function in your calculator. Just make sure you use the same calculator and know how to use that function properly so you don't mess yourself up. Alright? So how many atoms are there in 87.5 grams of iron? That's the same thing we just did? No. Oh, we're going the other way around. Alright. So we use the same conversion factor, right? But this time we have 87.5 grams of iron, and now we multiply by Oh yeah, we have grams, we don't have moles. So we got to go from grams to moles first, right? Because see here, okay, and I'm going to do this wrong now, just in case you have that, right? So if I use that conversion factor, I don't have grams, I have moles, and uh, I have atoms, right? So this is why I have the units, right? The conversion factor I have uh, 6.022 times 10 to the 23 atoms equals 1 mole. See, I have these units here and I've been writing them down. And it's important because I know I cannot do this. I have to have another step here in between. So I got to go from grams to moles. And there, of course, we have the molecular weight. And we know that 1 mole of iron from the periodic table is equal to 55.85 grams. So before I do that, I then need to take the 87.5 grams of iron and multiply by 1 mole of iron divided by 55.85 grams of iron. And then my next equation is I divide by a mole, 1 mole, and I multiply by Avogadro's number, 6.022 times 10 to the 23 atoms. So it's asking me for atoms, and so that should be the right answer, and I get 9.43 times 10 to the 23 atoms of iron. Alright, let's make it difficult. This is one of the harder questions. I like putting hard questions on the exam where you have to really think about everything. Okay, so we have an aluminum sphere containing 8.5 times 10 to the 22 aluminum atoms. Okay, so we know the number of atoms. There's a conversion factor from atoms to moles. Okay, so we must keep that in mind. So what is the sphere's radius in centimeters? Okay, and then it tells us the density of aluminum is 2.7 grams per cubic centimeter here. Okay, so then I give you a volume formula here of a sphere, and I'm asking for radius. So that's the first thing. So I have a formula that I have the radius for, and with a little bit of algebra I can solve that for R. Okay, and then I'm also given the density, and the density contains a volume. Okay, so I can probably figure out the volume from the density of this stuff. Alright, so what do we have? We have conversion factors. We have 1 mole of aluminum equals 6.022 times 10 to the 23 atoms. I also know that 1 mole of aluminum equals 26.98 grams of aluminum. Now from that I can probably figure out the volume, okay, from the density and the mass. Okay, all right, so if I have 8.55 times 10 to the 22 aluminum atoms, and I convert that to 1 mole to moles, 1 mole of aluminum divided by 6.022 times 10 to the 23. Alright, so I'm converting atoms to moles, and now I convert moles to grams times 26.98 grams of aluminum divided by 1 mole of aluminum I get 3.83 grams of aluminum. Okay, that's something. From there and density, I can get to the volume, right? So volume is going to equal mass, mass over density. So I take that 3.83 grams of aluminum and I divide it by that density, 2.70 grams per cubic centimeters, which gives me a volume of 1.42 centimeters cubed, which is a volume, right? So, and then I take this formula and plug it in for V and I solve for R. So that's going to be actually the cube root of V over 4 pi of 3 times V over 4 pi. Okay, and when you plug that in and use R is then 0.697 centimeters. Okay, so that was I encourage you to work a few of these problems from the end of the book. This completes chapter 1. See you in chapter 2.